so it's always a conditional. Conditional proof is such that the conclusion of the conditional proof is always a conditional, hence the name conditional proof. Right? Go back over here, right? It's always, what's the form of the rule, right? The form of the rule is such that the conclusion of the rule is always a p hook q. That is always a conditional. Since p and q are central variables, any conditional can be the conclusion of a conditional proof. Now, so you're looking at this, the conclusion of the rule, right? The thing you are tasked with deriving. That's what you're looking at when you say to yourself, this is the formula you're looking at the conclusion, not something you're already given, not something you're given, but what you need. This is the conclusion, this is what you're looking at when you have the thought, oh, I'm probably going to use a conditional proof, right? And this, the structure of this, what the antecedent of this is, and what the consequent of that is, that of the conclusion. That's what tells you what goes here and what goes here, okay? So, mistake in applying conditional proof is thinking, oh, I've got a conditional up here where the antecedent is A or B. Maybe what I should assume should be A or B. Or maybe you just write that down without thinking about what you're doing. You're lost. Because if you put A or B up here, that's your P, and the conclusion of your rule cannot be what you need your conclusion to be, right? If the assumption is A or B, right, what you're going to be entitled to infer using this rule is A or B hook something, right? The antecedent is going to be A or B. And it might even be this whole thing. But what use is that? Why are you using this rule to derive what you are already given? You're given if A or B, then C and D. So why are you using conditional proof to derive that? Don't use conditional proof to derive premises. You're given premises. You don't need to derive them. You need to derive the conclusion. And the specific conclusion you need to derive is A hook C. So what do? You just assume A, and very, 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 very crucially, you know that this subproof will end when you have derived C, okay? This is very simple, and you'll hear it, and you'll say, oh yeah, I get it, but it's just a matter of also knowing it in the context of an exam, right? You look at your conclusion, so you say, okay, it is a conditional, that means I'm going to use conditional proof. What is its antecedent? That's my assumption. And very crucially, what is its consequent? That is the conclusion of my subproof. That's the last step in my subproof. As soon as I correctly infer C from A, right, using this premise which you're given, right, you're now playing with these two formulas. From these two formulas, you're going to be able to derive C. And when you've done so, boom, that's the end of the subproof. Now you're back on the main line with the thesis A hook C, because that's what you've proven. You've proven that if I assume A, I can derive C. Therefore, if A, then C is true. And that's the conclusion you're asked to prove. Okay, so that's it. It's all about the structure. And that's a simple thought, but as you'll see when we do more complex examples, which will involve subproofs within subproofs, within subproofs within subproofs, right? Like I'll show you. This is the kind of thing you're going to have to be able to handle, right? This is page 187, right? You see that? Look at all those subproofs. Okay, all inside each other, right? And we will do that later. But knowing what formulas to write down where and in what order is just a matter of always applying this rule. Look at the conclusion and let the structure of your conclusion determine what assumption you make, and when it's a conditional proof, what formula will mark the end of that particular subproof. Okay, so when it's conditional, antecedent is what you assume, and always write down the consequent at the end of the subproof, leaving space to get it. Okay, you do that, that's those who do well, those who do poorly. The big distinction between them is those who can and those who cannot apply this simple thought. Okay, so boom. When we've set up like that, that's the only new things that involve, that's everything that's new to the use of this rule, conditional proof. Now, it's just as if you have these two premises, right? You do have these two formulas, and you just apply all the old rules you know, inference rules of inference, rules of replacement, to get C from A, and then you just complete the annotation of the proof, which is the rules justifying each step and the steps used. Okay, so what have you got? Okay, I need to get C. Okay, C's over here is the consequent of this conditional. I've got A. Oh, I can use my add trick. Right? A or B, justification, 1, add. Nothing wrong with this. Nothing wrong with appealing to premises inside a subformula. You can do that, as Klenk teaches you later on. When you're outside the subformula, when you're out here, after you've discharged the assumption and you're back on the main line, you may not appeal to formulas inside the subformula. For reasons which should be clear, given what I said before, all the things in the main line are absolutely true in the context of the proof, right? Given the premises, these things are absolutely true. That is not true under further assumptions. So what appears here has to be absolutely true, has to only rely on the premises and formulas on this line. You can't infer formulas on this line, where things are absolutely true, with the use of formulas which are only true under the assumption. Right? That would be illegitimate. Okay, but this you can do. This is more secure or more true under fewer conditions than these things. But you're given this as true, so you can certainly appeal to this here. Right? Oh, anyway. Excuse me. Didn't have that right. I'm adding to 2, right? Now I'm going to be appealing to, now I'm going to be using the first premise. I got 2, 3. Okay, so I'm looking at 1. I want to get the antecedent of that so I can derive, so I can infer by modus ponens C and D. Right, so I just add to 2, right? A to A hook B, that gives me 4 C and D modus ponens 1 and 3. Excuse me. Now is where you apply all the thoughts I mentioned before, right? Where you're now appealing to this premise, perfectly fine to appeal to this premise in deriving things within the subproof. You can appeal to premises when you're inferring within the subproof, but when you're outside the subproof, back on the main line, you may not appeal to formulas within the subproof. And if you're clear on that epistemological difference, as it were, right? These are absolutely true. These formulas are only true under the condition. If you're clear on that, you should be able to see why. All right, so boom, we're almost there. Now I can infer C from this because simplification 4, that's it. I can simplify this. I've got a conjunction of C and D. I simplify this. Okay, so that's the last that's the last justification within my subproof, right? Because I did the right thing in the beginning, right? I looked at my antecedent, that was what I assumed, and I put my consequent down the bottom of the subproof, indicating, letting me know when I've come to the end of my subproof, when I get this specific formula, the specific formula that is the consequent of the conditional I'm trying to prove, right? Now I know I'm done, right? So 1, 2, 3, 4, 5. Step 6 is my conclusion, A hook C, conditional proof, 2 through 5. 2-5. I cite the entire subproof from the assumption through to the conclusion, and that's it. In step 6, when I move away from the subproof and back to the main line, in step 6 I am discharging my assumption, right? I've got my formula, that's it. We're done. A hook C, conditional proof, okay? The big lesson was, this is where you look to determine what formula to assume, A, the antecedent of what you're trying to conclude, and this is where you look to know what formula you need to put at the end of your subformula to know when you've finished. Conditional proof has a advantage over indirect proof, as we'll see in a minute. When you're setting up for indirect proof, you don't know exactly what formula. You don't have the specific contentful particular formula with which you're going to end your subproof. Because the form of conditional proof is, the conclusion is right? Q and not Q, so all you know about your conclusion is that it has to take the form of a contradiction, but you don't know what the Q is, right? Whereas it's different for conditional proof. The thing you're deriving is P or Q, so whatever the specific Q is, whatever the specific consequent of the conditional you're trying to derive is, goes here. So, goes here. Ends your subproof. When you're trying to derive not P, you assume P, you're going to be done when you find any contradiction, but you don't know what the contradiction is. So you don't have the specific formula which will end your subproof. That's a disadvantage, as it were, that indirect proof has over conditional proof. Conditional proof has that advantage. You know the specific formula which will end your subproof, namely the consequent of your conditional. All right, that'll end this part.